Welcome, everyone. Today, we're starting a discussion on Newton's laws of motion, which are fundamental to understanding how objects move and interact. These laws form the basis of mechanics, a key part of physics that explains the relationship between forces and motion. As we go through the material, you'll see how these concepts apply both in everyday life and in scientific contexts, helping us to analyze and predict the behavior of objects in motion. Let's begin by exploring these laws step by step.
Here, the net force is 5 newtons to the right. This is because we have a force of 10 newtons pushing to the right and a force of 5 newtons pushing to the left. Since these forces act in opposite directions, the net force is the difference between them, which means the object will move to the right with a force of 5 newtons.
Building on the idea of forces acting on objects, it's important to understand that an object won't change its state of motion unless a force causes it to do so. This principle is known as the first law of Newton, or the law of inertia. It means if something is sitting still, it will stay still, and if it's already moving, it will keep moving at the same speed and in the same direction until something else influences it. This helps explain why objects don't just start moving or stop moving on their own.
The car is moving at a constant velocity because the forces acting on it are balanced. If you look at the arrows, you can see that there is a 500 Newton force pushing to the right and an equal 500 Newton force pushing to the left. Since these two forces are equal in size but opposite in direction, they cancel each other out, resulting in zero net force. With no net force acting on the car, it doesn't accelerate. Instead, it continues moving steadily at the same speed and in the same direction. This situation illustrates dynamic equilibrium, where the object is in motion but the forces are balanced.
Building on the idea of constant velocity, now let's consider what happens when there is a net force acting on an object. Newton's second law explains this relationship by stating that a net force causes acceleration. The acceleration an object experiences depends directly on the size of the net force. More force means more acceleration, and inversely on its mass, so heavier objects accelerate less for the same force. Importantly, the direction of the acceleration matches the direction of the net force applied. This is summed up in the equation F equals ma, where force equals mass times acceleration. This concept helps us understand how forces cause changes in motion, such as speeding up, slowing down, or changing direction.
Let's move forward and talk about how to apply the formula F equals ma. This equation shows the relationship between force, mass, and acceleration. If we rearrange the formula to find acceleration, it becomes acceleration equals the total force divided by mass. Similarly, rearranging for force, we have force equals mass times acceleration. In terms of units, force is measured in newtons, mass in kilograms, and acceleration in meters per second squared. For example, if a 2-kilogram object is acted on by a force of 10 newtons, it will accelerate at 5 meters per second squared. This helps us understand how forces cause changes in motion based on the mass involved.
Now let's take a closer look at free body diagrams, or FBDs. These diagrams show all the forces acting on a single isolated object. We represent the object simply, often as a dot or a box, to keep the focus on the forces. Each force is drawn as an arrow pointing away from the center of the object, indicating the direction the force is applied. It's important to include only the forces acting on the object, not the forces the object exerts on others. Using free body diagrams helps us identify the net force, which is essential for analyzing the object's motion. For example, in the diagram here, you can see 4 forces: the normal force pushing up, weight pulling down, friction pushing left, and an applied force pushing right. Keeping all these forces clear makes it easier to understand how the object will move.
Now, let's take a closer look at Newton's third law, which tells us that for every action, there's an equal and opposite reaction. This means forces always come in pairs, where one object pushes or pulls on another, and the second object pushes or pulls back with exactly the same strength, but in the opposite direction. These forces act on two different objects, so they don't cancel each other out, but instead interact with each other. The magnitude of these forces is the same, but their directions are exactly opposite. You can think of it as if object A pushes on object B, then object B pushes back on object A just as hard, which is why objects respond in predictable ways when forces act on them. This principle is fundamental in understanding how things move and interact in the physical world. Let's look at some practical examples of Newton's third law to better understand how it works in real life. When we walk, our foot pushes the ground backward and the ground pushes our foot forward, allowing us to move. Rocket propulsion is another example, where the engine pushes gas downward and in reaction, the gas pushes the rocket upward, propelling it into space. In the recoil of a gun, the gun pushes the bullet out and the bullet pushes back on the gun, causing it to recoil. Swimming works similarly. The swimmer pushes water backward with their hand and the water pushes the swimmer forward. These examples clearly show that for every action, there is an equal and opposite reaction. The apple falls because the earth pulls it downward with a force we call gravity. This force is strong enough to overcome the apple's connection to the branch and pull it toward the ground. Importantly, the matching force, or Newton pair, isn't the air resistance that slows the apple down as it falls. Instead, it's the pull of the apple back on the earth. Even though the apple is small, it exerts a gravitational force on the earth, just like the earth pulls on the apple. This mutual attraction is a key part of how gravity works between any two objects. Let's take a moment to address some common misunderstandings. First, motion itself doesn't need a constant force. It's only when an object is accelerating that a force is required. Next, action and reaction forces don't cancel each other out because they act on different objects, so they don't simply nullify one another. Also, heavier objects don't fall faster than lighter ones when we ignore air resistance. Lastly, inertia is often mistaken for a force, but it's actually a property of mass. It's how much an object resists changes to its state of motion. These points help clarify how forces and motion really work. When there are no net forces acting on an object, it remains in equilibrium, meaning it either stays at rest or moves at a constant speed in a straight line. This is what the first law tells us. The second law explains what happens when there is a net force. It causes the object to accelerate, with the acceleration being proportional to the force and inversely proportional to the object's mass. Lastly, the third law highlights that forces always come in pairs. If one object exerts a force on another, the second object exerts an equal and opposite force back. These three laws together help us understand how objects move and interact in everyday life.